Can you hear me? Yeah.
Yes.
So, hi, I'm Marion from. My pronouns are they, them. I'm a PhD student at the University of Glasgow, and my background is in quantum optics. My PhD involves experiments in rotating frames to probe the question of how quantum mechanics and gravity interact. Quantum mechanics usually describes very small scales. The quantum world is full of weird phenomena like wave-particle duality, superposition, and entanglement. Nevertheless, these strange quantum effects now underpin much of the technology we take for granted every day. Even the humble USB flash drive relies on quantum tunneling. From quantum theory emerges the standard model of physics, covering 3 of the fundamental forces, but it doesn't say anything about gravity. To understand that, we turn to Einstein's theory of general relativity. Gravity is the curvature of spacetime by matter and energy. General relativity covers the most massive scales and has its own share of weirdness: black holes, gravitational waves, even in theory, wormholes and time machines. But GR is still relevant here on Earth. GPS systems couldn't function without it, so there'd be no Pokemon Go without Einstein. These theories are super powerful. Between them, they cover almost everything, yet they're completely incompatible. To simplify massively, GR wants the universe to be smooth on all scales, whereas QM says everything is chunky. QM is probabilistic, events have multiple random outcomes, while GR is deterministic, there's a single outcome. When we try to combine them, quantizing GR or scaling up QM, a lot of the maths stops making sense. For example, calculating the vacuum energy density with QM, first done by Zeldovich, more from him later, infamously gives answers up to 120 orders of magnitude bigger than observed. These theories really don't like each other. So what's my approach? I'm not trying to invent a new quantum gravity theory of everything. Better physicists than me, no doubt some in the audience, are already doing that. But when faced with uncharted territory, you shouldn't only theorize about what's out there. You must also step out and see. As someone with a non-binary gender, I'm rather familiar with the middle ground between supposedly opposite things. Just because it makes some people uncomfortable, that middle ground doesn't simply stop existing. There's little consensus on how to make gravity quantum, yet we may not need that to test the slightly easier question of, is gravity quantum? If we can, for example, generate quantum effects like entanglement from interactions that are solely gravitational, it would prove gravity must be quantum somehow, itself a huge step forward, plus providing experimental backing for quantum gravity theories across the board. We don't need a theory of everything just to test situations where both QM and GR are required and start mapping this territory. The first step I made was the first verification of an effect related to both black holes and amplification from the quantum vacuum. The Penrose process is an idea to harness a rotating black hole as a power source by dropping an object into the ergosphere where it can have a negative energy and losing part of it into the black hole. The remaining part, having lost negative energy, can be retrieved with a net energy gain. Zeldovich then predicted EM waves with orbital angular momentum, OAM, could be amplified in the same way, not just by black holes, but by other rotating absorbers, like this metal cylinder. The process should also amplify waves out of the quantum vacuum, similar to Hawking radiation. The cylinder sees these OAM waves to be rotationally Doppler shifted. Their frequency changes depending on the rotation speed, similar to the linear Doppler shift. Normally, the metal partly absorbs the waves, but if the cylinder rotates fast enough, then the Doppler shifted frequency goes negative. This sign change forces the absorption to become amplification, and the reflected wave gains energy from the rotating cylinder, like taking energy from the black hole. We proved this using sound waves. We used a ring of speakers to create a sound wave with OAM and directed it towards a rotating foam absorber. and microphones that measure the Doppler-shifted waves that pass through. This is the data that we recorded. As the rotation increases, the frequency is Doppler shifted to 0, where it gets too low to hear, and then it gets louder again with increasing negative frequency. We can play back the sound heard as the rotation ramps up and extract the amplitude to see the amplification. The signal is distinctly larger after the Doppler frequency has gone from positive to negative. We can compare this with sound through non-moving foam, where there's only absorption. The amplitude of the negative frequency waves is much larger when the absorber is rotating, proving they take energy from its rotation. But why sound waves? Sound isn't quantum, and sound and vacuum don't go together. The condition required just makes it very difficult with light, because the speed of light is so much bigger than sound. You either need to spin at near optical frequencies or have a slow experiment that could be kilometers wide. We hope the proof of this surprising effect with sound will encourage new experiments with EM waves and quantum fluctuations. Indeed, we're working on one EM test with our collaborators in Southampton. Meanwhile, I've been working on different stuff that is very much quantum. I want to see if we can use rotation to change or even create quantum entanglement. Why? The end goal is to test GR effects, but to see those, you generally need big distances and planets or black holes. It's quite hard to put those into a uni lab. But we can use Einstein's equivalence principle, the equivalence of curved spacetime to non-inertial motion. Linear acceleration can be a pain because your experiment doesn't stay in the same place. But for circular acceleration, you just build an experiment that spins. Currently, I'm trying to use uniform rotation to alter quantum entanglement. The heart of my experiment is a Hongu-Mandel interferometer, or HOM. This is a way of seeing how similar two photons are. When two photons meet at a beam splitter, there are 4 possibilities, depending on whether each is reflected or transmitted. But if the photons are indistinguishable, destructive quantum interference ensures they always bunch and leave the beam splitter together. Detectors in the output ports together measure coincidences when they both detect a photon. Time delay between input photons introduces distinguishability. So scanning this delay, we find a characteristic HOM dip where they overlap in time. This can be used for very precise time and distance sensing. If the visibility is over 50%, the input light is quantum. Even better, a HOM can be a witness for entanglement. If you see a peak instead of a dip, then this can only happen when your photons are in an anti-symmetric entangled state. If you see a dip, they could be symmetrically entangled or completely independent. My experiment builds on our team's previous setup that used rotation to change the delay between photons in a HOM. A symmetrically entangled photon pair is produced at this nonlinear crystal. They travel opposite ways until they interfere. Rotation induces the special relativistic Sagnac effect, where the invariance of the speed of light in the non-rotating frame means it takes different times for the light traveling with and against the rotation to complete one loop. The delay increases with the rotation speed, and this caused our HOM dip to shift with rotation as the co-rotating photon was delayed with respect to the other. By adding extra paths so each photon in the pair experiences a superposition of co- and counter-rotating motion, the Sagnac shift no longer changes the delay between the photons, but instead changes the phase of their entanglement, changing it from symmetric to anti-symmetric with rotation speed. By observing a dip turn into a peak, we'll show we can change and reveal the photon entanglement through rotation alone. It's currently in progress, but we do hope to put out a paper on this soon. To summarize, by combining rotation and quantum effects, we can start to build a bridge between general relativity and quantum mechanics. In the future, we hope to take the ideas further with a new experiment where rotation would actually generate entanglement. Thank you for listening.
Thanks very much. Are there any questions from the audience? I'll give anybody a chance to type one. I have a quick question about the experiment that you just mentioned. What sort of timescale do you think it's likely to be before you manage to get an experiment like that set up? Is that within a PhD or is that longer term?
So you mean the rotating
Yes.
experiment? I mean, this is it here.
Oh, okay. I'm sorry.
So the data we've got so far is still a bit noisy, but
Okay.
we have some data, so we're hoping to write a paper soon.
Okay.
But yeah, it's been because we already had like most of the setup to kind of adapt it. It's taken me, I don't know, the past 2 years, but there was a pandemic. So.
Okay, well, I'm sure we will all look forward to reading the paper when it comes out.